Okay, good morning. So today I'm going to talk to you about this work that I did during my master's, working on developing an evolutionary optimization framework for the SpiNNaker Neuromorphic hardware platform. So we're in SB9, and just sort of give you an overview of the next 7 minutes of your lives. Going to look at the motivation, why this is interesting, why this is important, why I did this research. Then I'm going to talk a little bit about evolutionary algorithms in general, and genetic algorithms and where they fit within that. Then I'm going to talk about the experiments I did, implementing this and running models on SpiNNaker. And then I'm going to talk a little bit about the conclusions from this research and the future work and sort of what I'm doing now. Okay, so this is the SpiNNaker machine we have in Manchester. In last November, we just hit the total of having 1 million cores, and it can be used to, amongst other things, simulate spiking neural network models. Now, there's two problems with spiking neural network models. There's two main sources of them, really, that you might want to sort of investigate using SpiNNaker. And there's the biological models, which come from neuroscience. The problem with these is that often the parameter sets are not fully defined. So there are limitations in terms of experiments, be they just experimental limits, the limit of resolution of fMRI, for instance, or ethical limits. You can't just measure all variables at once. And also we're looking at machine learning models that come from machine learning. And converting artificial neural networks to spiking neural networks is not a trivial task. One of the great things about evolutionary algorithms is that they're highly parallel. I'll talk a little bit about that in a minute, but with the size of the SpiNNaker machine, it means that we can do lots of things in parallel rather than doing lots of sequential models, and that sped this up quite significantly. So here we have the general structure of an evolutionary algorithm. You have a population of models. So don't get confused here with if you're used to using perhaps Pine or something like that, a population of neurons. This is sort of a level of abstraction above that. This is a population of models. So you generate a population of models, then you evaluate them against some fitness function. And then if the models are fit enough, if they're to your standards, really, you accept them. And there's your optimized population. And you can take the best models, the best networks from that population, and you've optimized them. They're optimized models. Now, in the case of genetic algorithms, the population is usually more than one. There are other evolutionary algorithms, and I'll mention them a little bit later. But in mine, I simply took a population, the initialization of the population I'll mention in a minute, but then I would run it through, evaluate these models, select the top 10, sort of clone them up to make sure that no models were lost, no networks were lost, do some variation, some genetic crossover and some mutation, and then evaluate again and keep going around the loop. So the genetic algorithm that I used had a population size of 24,000 and a mutation rate of 0.1%. This came from sort of figures that are available in the literature. I'll give my references at the end. And in terms of the crossover, this was 2-point crossover. So I have a gene that represents the neural network. I'll show you that in a minute. But just to get the idea that there is information moving between models. So yes, this explains it a little bit better. So the network that I used to test the framework was doing MNIST digit recognition. This is a standard machine learning task. And the point of this research was not to get a very good score on MNIST. The point was to show that there was improvement and that evolutionary algorithms can, on this scale, work to improve models. So yeah, I had this simple convolutional spiking neural network, and the weights here were encoded into a gene that looks something like this. The first 25 were the filter for the first bit here. There's quite a lot of dependence on the filter, so we'll talk about that in a minute. and the output weights in this fully connected layer here. And just to make the problem size even smaller, I restricted the weights to values of -1, 0, and 1. So really it's more talking about structure than anything, more than weight tuning. And I had two populations, a seeded population that had this sort of center surround type filter that's a bit like a Mexican hat that we saw yesterday. And I also had an unseeded population. This was just randomly generated. And these are the results. So as you can see here, there is some improvement. This is looking at the whole 24,000 in each generations along the bottom here. And we can see some improvement. Now, this is a bit of a strange way of doing this. This is the training accuracy on here is a legitimate metric because you've got each generation sees 60 images, one of each digit class. And as you can see, there is improvement up to here. So the best one came out about over 80%, which is good for MNIST. But then I then tested it against the testing set and got something about 66% for the unseeded population and 63% for the seeded population, which is what I expected because there's more variation in the random initialization in the unseeded population. And going on to future work, so this was really just a test case. This example network showed that there was improvement and that you can use genetic algorithms to tune spiking neural network models on SpiNNaker. And the advantage of doing it on SpiNNaker is just the amount of parallelism you can do. I could run 24,000 models near simultaneously. And some sort of avenue for interest is the different evolutionary algorithms. So there are evolutionary strategies is a slightly more improved version of genetic algorithms in the sense that it uses real values and can direct the evolution process rather than just randomly changing things. I'd like to run evolutionary algorithms directly on SpiNNaker. This was using a server and then evaluating models on SpiNNaker and then drawing the data back, and there is an overhead related to that. I think that maybe further down the line this has some impact in changing the kind of workflow involved in SpiNNaker. So we've got this this cycle here that you design a model, you upload it to SpiNNaker, run it on SpiNNaker, and then you download the data for analysis, do some thinking, change the model. In the future, I think it would be possible to have a less well-defined model, and the optimization will be done on SpiNNaker and would allow you to have a lot more freedom in terms of variables and the definition thereof. And what I'm working on more directly at the moment is converting artificial neural networks. These are machine learning models from deep learning and that kind of thing, to convert them to spiking neural network models, which is, as I say, non-trivial. But I think there could be some application for optimization and evolutionary algorithms for tuning the models that come out of this process, or even tuning the process itself. So with that, I'd like to say thank you, and any questions? We'll probably take questions at the end.